Hello again. This is session number 3 on dimensioning according to the British standard BS8888. There are a couple of points we need to remember before we start dimensioning according to the British standard. The first one is dimensions should be clear. It shouldn't be very small. It should comply to the British standard in terms of sizing, in terms of position, in terms of line types, and so on. So dimensions on your drawing should be enough so that the manufacturer or whoever is manufacturing the component does not have to scale dimensions or rely on dimension deductions from your drawings. It should be clear and easy. Dimensions should appear only once in your drawings. You don't need to duplicate it. So no double dimensions. And we should avoid dimensioning hidden detail lines. That's why we use sections. So we never dimension hidden detail lines, but we use sections to reveal them, as you will learn here in this later in this lecture. And also for assembly drawings, we should only just include overall dimensions. Okay. So what you see on here is like a view, could be like a front view, for example. And this is an example of dimension lines. See, for example, this is a dimension line for this slot here. This is another dimension line here to show the distance between these two holes. Here, a dimension line for the diameter of this hole here. Another dimension line. This part, this arrow and this arrow defines the distance from the edge to the center of this hole. There is a rule also when you include dimensions in your drawings. This rule is that larger dimensions should be placed outside smaller dimension lines. Look at this example here. You see the larger dimension, which is the 90, is outside of the smaller dimensions, which are like 3, 50, 12, 6, and so on. So you cannot swap these two. You cannot just say, for example, the distance from here to here is 90, and then you place the 90 here, and then you put all these small dimensions at the outside. This is wrong. You should you should use the larger dimension, or you should place the larger dimension outside of the smaller dimension lines. Also, dimensions should be placed on the view or section that shows the relevant features clearly. For example, here, if you look at these two views, and you see here, for example, for this hole, the dimensions are shown on the on this view. So the diameter of the hole is shown here. The location of the center of the hole is shown by this dimension 11 from this edge and 7 from this edge. So it's more clear if you just add the dimensions for the hole here on this view, not on this view. Also, for example, the width of this slot here, of this cutout here, more clearly can be defined or placed on this view rather than on this view. The 6 millimeter, the height as well, it's easier and clearer if you add it to this view. Similarly, this here, you have two views again, and then because this circle here, this circle is just, it is being cut here at this point. So the distance between this edge here to the diameter is, or the end of the circle is 60 millimeters. So it's clearer to define it here. Here you can define the diameter of the circle itself on this view, the diameter of the, because you have different circles here. So it's easier if you define the diameters on this view rather than on this view. But for this one, for this particular one, because it's been cut here, so it's easier to place the dimension on this view for the 60 millimeter dimension. Also, whenever possible, dimensions shouldn't be placed within the contour of the depicted item. So, for example, here you see all the dimensions are placed outside of the item itself or the part itself. These dimensions, this one, this one, this one, and that one here as well, all the dimensions are placed outside. So if you were to add this dimension here, for example, at this location, and add this dimension uh, somewhere here, and then add this dimension somewhere here, and it is included within the contour of the part, it will be more confusing. So it's better if you just add or place all the dimensions outside of the part. So this view here, or these drawings here, shows you the various elements of dimensions that should be included or illustrated in your drawings. These definitions are quite important for you to understand. So number one, for example, this is called the dimension line. This is your continuous, like line, continuous narrow line, if you want, which is the dimension line. Number two here is the value of the dimension itself. Number three is the terminator, which is in this case, we use a solid arrow here for the British standard. Number four, these lines are called the extension lines. If you are using this for as follows, for a circle, for example, or an arc, it's called leader line, number five here. Number six is the reference line, which is this horizontal line here, reference line, where you might need to write a number here. For example, the diameter of this hole, similar to here, phi 4. This is the diameter of this circle. Phi is 4 millimeter. Phi 4 is the diameter of the circle. Then number seven here, the origin symbol. So this is, for example, if you use this kind of continuous dimensions style, so you should start at some origin, and this circle here defines that this is the origin, where from here to here is 10, and then from here to here is 30, but everything starts at this origin. Number eight, this one is the property indicator. Sometimes you need to say that this is a radius or this is a diameter and so on. And number nine here is a reference letter. So you might just need to include some text here or something according or related to this feature. So dimension line of a broken feature. If you have a broken feature, you still have a continuous narrow line for the dimensions. So if the feature itself is broken, so the dimension line is shown as unbroken. Maybe this is better shown by this drawing here. So for example, this is only, consider this is only the bottom half of a part. And then what you see here is kind of, if you have a broken part, meaning that if this part is very, very, very long, and for example, between this edge here to this edge here, maybe there are, this distance here is quite long, okay, but with no details, with no features on it. It's just continuous. It's the diameter, the distance between here to here doesn't change. So instead of showing this very, very long component on the sheet of paper, we just use this broken line. But in this case, if you use broken line to just show here a part, the dimension lines themselves are unbroken. So they are just solid narrow lines as usual, and you add the real dimension here. What you see here is called the parallel dimensioning. You see here this line, this dimension line, this dimension line, this dimension line are all parallel. So parallel dimensioning means that it consists of a number of dimensions They are all originating from a datum. So if this is the datum, see, so this dimension started from the datum, which is here. This dimension started from the datum, which is here. This dimension started from the datum, which is here. So when you start all the dimensions from the same datum, so this is what's called parallel dimensioning. On the other hand, we have another type of dimensions, which is called chain dimensioning. Chain dimensioning, see, they are just coming in series, like this one followed by this one, followed by this one, followed by this one, followed by this one. So in chain dimensioning, they should be only used where the accumulation of tolerances does not affect the function of the part. Because in parallel dimensioning here, for example, they are all measured, or they are all, so the reference line is the datum here. They all start from here. So they do not affect each other. So the tolerance here and the tolerance here and the tolerance here, they do not add up. But here, the tolerance on this dimension is going to move this edge to the left or to the right based on the tolerance here, and it's going to affect this dimension, and the tolerance will just keep adding up. So if you are worried that the accumulation of tolerances is going to affect the function of the part, do not use the chain dimensioning, but rather use the parallel dimensioning. What if we have holes? So see here, the dimension line of a hole, for example, for this one, the dimension line here is oblique, so it goes through the center of the hole, and we have this kind of leader line and a reference line where we say 2 times phi 18 means that we have 2 circles. So this is one, this is another one, and then the diameter of each one, they have the same diameter. So and the diameter is 18. So you just place the dimension here or add the dimension here to one circle only. You do not add it to the second one, because here 2 times means that you have these two, they are identical. So you do not need to repeat the dimension for this circle here. Also, you can use leader lines. So for example, here the leader line is used for this small circle, but it should the leader line, if you extend the leader line, it should go through the center of the circle. Or you can, for example, show it like this. If the space here allows you to add this phi 10, so you can just add it here within these two lines, these two extension lines, or you can just draw a solid line here. This is the dimension line, and you write this on top or within the circle itself. So different dimensioning, acceptable dimensioning for holes, depending on the size of the hole. You can also use leader lines to dimension several features. For example, you have, this is 25 mil, but if you were to just draw the dimension here, it's going to be within the contour of the part. It will be confusing. So you can just simply, if you don't have another view here, you can use these lines, leader lines, to show the dimensions for 1, 2, 3 circles, for example. But for the top one and the bottom one, it's better if you show it like this. If we have other features like arcs, for example, so dimensioning of radii of arcs, it depends on either you need to identify the location of the center of the arc or not. So for example, if you look at figure A here, it is required to identify the location of the center of the arc. So that's why we use this kind of 2 center lines intersecting at the center of the arc. And then we use this dimension line and then the leader here to say this is R8. The radius of this arc is 8. The same is here, for example. So you can just, the arrow could be coming from the center to the arc, and then you write it outside here, or the arrow can be like this coming from outside. So either this or that one, they are both acceptable. If the center of the arc is not important or is not required, so you can use this kind of dimensions. Like for example, here you can just use like an arrow and say this is R 5.5 without if it will be like deducted from the location itself, or it's not needed. So you say here this is R 5.5 without like identifying the center. This is R4, this is like R4, this is R25, and this is R1600, and so on. Also here, we've just explained these ones, but also here, for example, if you look at this view here, you have 1, 2, 3, 4 holes. So instead of just dimensioning each and every one, we can just add a dimension line here and say 4 holes 5, or this could be cross 4 cross 5. So it shows that these 4 holes, they are identical, they all have the same diameter. For example, here, this dimension line shows here, or this leader line here shows that the diameter of this hole is 9.5, and it is 18 millimeter deep. So the depth of this hole is 18 mil. On the other hand, for a different part here, we have, for example, the diameter here is 5.7. See, it's difficult to write it in here, so that's why you write it outside, and you can define the depth. If there is like some tolerances to be included, you say like 13 plus 0.5 is the upper tolerance limit, and 0 is the lower tolerance limit. The same here is like 5.32, and then the upper and lower limits are identified as well. For chamfers, it depends on the either they are for the angle of the chamfer is 45 degrees or not. Normally, when the angle is 45 degrees, it's easier to dimension. So, for example, if we have external chamfer, see this one, we have an external chamfer here, and it says 2.5 times 45 degrees. So what you do here, the distance between these two lines is 2.5 mil, and the distance between this corner and this corner, this corner and this corner in the vertical direction is 2.5 as well. So if you were to draw here a triangle at this corner here, so the triangle will have a distance here which is 2.5 in the horizontal direction, another distance here which is 2.5 in the vertical direction, and then if you connect these two points together, or these two corners together, it gives you 45 degrees. And this is the way you dimension them. It's just say 2.5 times 45 degrees, or you can just say you can dimension it like this, so where you have this leader line, or you can just say the distance between these two lines is 2.5, and the angle here is 45 degrees, and this is for external chamfer. For internal chamfer, we have more or less similar kind of designation. You say like, so the extension of this line, which is this extension line, and then this is your leader line here, and say 2 times 45 degrees. 2 here means that if you draw here a triangle, so the width, the width here and the height, the edge, this edge and this edge, they are equal and 2 millimeter each. Or you say the distance between these two lines is 2 millimeter, and the angle here at these two corners is 45 degrees. But if the angle is not 45, is not equal to 45, so we should indicate this clearly. For example, for external chamfer, we say, okay, so the distance between these two lines is 2 millimeter, but the angle here is 30. And the way you do this, for example, you have this line, and then you draw a parallel line that is away from this line by 2 millimeter, and then from this corner, or from this corner rather, you just draw a line. This line has an angle of 30 degrees with the horizontal, and you do the same here. You draw a line with a minus 30 degrees with the horizontal. Here you can define this diameter and the angle, and these two is going to define actually the chamfer here. If you have internally chamfer, the same again. If you have the distance between these two lines and you have the angle, you define them like this, or you can say the angle here, the total angle between these two lines, if you were to draw the angle between them, is 60, and the distance here, or the diameter of this hole here, is 40 mil. The next is screw threads. See here on the left-hand side, we have external screw threads. So this is like the threaded part. Normally, the threaded part is drawn as two parallel lines. The external one is wide, and the internal one is narrow. So this is thick, and this is thin. And again, this is the external one is thick, and the internal one is thin. The lines that shows the end of the thread is thick again, and these two lines are thick as well. So there are some dimensions here we should understand. So you might need at some point to read this note carefully, but the way we define the threads is like, for example, you say M 20 times 2. So M here refers to isometric screw thread, and then the number that is written after the M gives you the nominal dimension, the nominal diameter of the thread, or the external diameter, times 2. 2 here gives you the pitch of the thread itself, and they are in millimeters. So for example, if you read this note, M8 times 1, M is isometric screw thread, 8 is the nominal diameter of the thread, and 1 is the pitch in millimeter. Okay. For example, here we have M36 only, so we don't have the times 1 or times 2. If you don't have the pitch written here, so it means that we have what's called a coarse pitch, and there are some tables for that. But for example, here for M8 thread, the coarse pitch is 1.25. So M36 here means that it's coarse thread, and then we need to find the based on tables, we need to find the pitch for coarse pitch. Okay. Also, you see here, you'll find like 6G written here. 6G here gives you the tolerances, the upper and the lower tolerances of this external thread. And we're going to talk more about the threads, and you will get to understand what is GH and those numbers. But for now, consider that this 36 is like having like our upper and lower limit for tolerances. Also, we define here some dimensions for the length of the thread, which is the distance between here to here is 30 millimeter. The distance between here to here is 38 millimeter maximum. And this area, or this part here between this minimum and maximum dimensions, called the run out, which should be defined as well. So the depth, or the thread length should be defined using kind of the minimum maximum dimensions, including what's called the run out, which is this area here between these two dimensions. If you have internal thread, on the other hand, again, you have M12, for example. So M12 here is like isometric thread with a nominal diameter of 12 mil. The 7 capital H here, so for internal, for holes, we use capital letters for tolerances. For shafts, we use small letters for tolerances. You will get to know more about this by the end of this lecture. Then here we have 15 minimum fall thread. So they are talking here about the height, the length of the thread itself. here, this one is defined as M12 times 1.25. So the pitch is defined here. The pitch is not defined here, meaning that it's a coarse pitch, and we should find out based on tables the pitch for this one. The depth here, see, because we have before we create the thread, we use a drilling tip first to make a hole. So what you see here inside with this part here, it's the end of the drilling tip, and then after that we start the threads. Okay, so using another tool. So in here, for example, it is defined as M6 6H. So the 6H is like relating to the tolerances that we'll talk about later, but M6 here meaning that it's isometric screw thread. The nominal diameter is 6 millimeter. The 20 millimeter and the 28 millimeter minimax, similar to this one, that defines the limit or the length of the thread. If you have like kind of angular spacing, so this is how you dimension them. You have here, for example, these holes are placed or located here equally. So you can just say from here to here, we have 5, which is like we have 5 distances, 1, 2, 3, 4, 5 distances. And the angle between this center line and this center line is 10 degrees and 30 minutes, which gives you in total 52 degrees and 30 minutes. So this is how you dimension like angular equal spacing. On the other hand, we've just spoken about this before, but if you have identical features, like for example, here you have 4 holes and they all have the same diameter. So we can just simply pick one of them and say 4 times phi 10, meaning that the diameter of this hole and every other like hole in the 4 of them is having a diameter of 10 millimeter. The same for this arc, for example. So that says this arc will have 4 times R6, so the radius of this arc is 6 millimeter, and we have 4 of them, 1, 2, 3, 4, and each and every one is having the same kind of radius. About extension lines, there are some like rules for extension lines, some notes to remember. First, extension lines are these lines, these vertical lines here. Okay, they all shown as continuous narrow lines, again similar to the dimension lines. Extension lines should extend beyond the dimension line. So if this horizontal one is the dimension line, you see the extension line is going beyond the dimension line a little bit. Obviously, it should be 8 times the line width that we use. Also, there should be some sort of a gap here between the extension line and the feature itself. So it begins a little bit after the edge. So it doesn't touch the edge. You see, there is a gap here, small gap here, small gap here, small gap here. So you should remember these. It's the first, it's continuous narrow line. It should extend beyond the dimension line. There should be a gap between the feature and the line, the feature and the extension line. Extension lines could be oblique, but if you choose to do that, they should be like parallel. So for example, if you were to define this diameter here using these 2 extension lines, and if chosen this oblique extension lines, so they should be parallel. This one and this one, they are parallel to one another, and the dimension between them shows the diameter. And for example, these 2 as well. These 2 extension lines, they are parallel to one another, and then they define the diameter between this point to this point. what if we have angular dimensions with can be defined as follows as well. For example, if we start by this angle, so the extension line here should extend along the angle leg. So this is one angle leg, this is another angle leg. So the extension line, see, there is a gap here. It is extended a little bit beyond the dimension line, and then we have a narrow dimension line here with the angle of 83. Similar to here, we have something similar. So two extension lines with a gap here, with a little bit extension beyond the dimension line here, and the angle is written. And remember, the angles or the dimensions themselves are written above the lines here. Look, it's above the line, above the line, above the line, above the lines. We do not write the value between or within the line itself, and then it is from here to here, then it stops, then the dimension value, then from here to here and stops. We do not do that. We just write it above the lines. Thank you. This is the end of session 3, and next is session 4, indication for tolerance.